right. So as you can tell by looking at me, I've been doing this a long time. And I graduated from engineering college in I guess December 1978. So you do the math and you know about how old I am. So gosh, I've been with Harman doing loudspeaker systems. I can't count how many for the last 33 years. And before that, I was actually, I'm kind of going backwards, but in 1979, I gained employment in Vancouver, Canada, with kind of a mom and pop, father and son outfit, very small company that made a high-end loudspeakers. And I did that for 3.5 years. And then I gained employment at Plantronics in Santa Cruz as an electroacoustic engineer. And some of you may have heard of it. It's Plantronics. At that time, they were the leader in telephone headsets, and unfortunately, it was good for its time, but it wasn't industry in the long term I wanted to stay with. And in 1989, I was fortunate enough to get into Harman with Infinity Systems. And if you look up classic Infinity Systems, you'll find out in its heyday, Infinity was one of the leading loudspeaker brands. Really pioneered high-end loudspeakers. In fact, Arnie Nudell, who was the founder of Infinity, really created what is now, you see loudspeakers for hundreds of thousands of dollars, but he was the first to prove that there was a market for very large, 6-foot-tall, multi-woofer, high dynamic loudspeakers. I think at that time, the RS1 was about, was it $10,000 or $20,000 a pair, but in $1979, you're talking about $60,000 or more. Anyways, I sort of went all around of my current career, but I have a lot of slides to cover, and I probably will do as much as I can. We'll see if we can answer questions. If I can't, well, if there's no time, we can just email me, but let me know when we can start.
Perfect. Okay, yeah, I think we can go ahead and get started.
Okay.
We have until the end of the hour, so however you'd like to use the time, or however you think is most productive. But yeah, thanks again also just for doing this.
Oh, sure.
I know there's like a bunch of information, so yeah, I sent out an email, so hopefully you guys all got to read a little bit about Mark, but
okay,
yeah, we're gonna learn a lot.
Cool. Let's go ahead and start. And I have a share screen. Do I press the share screen or?
Yeah.
Okay.
And then it should ask you which screen you want to share.
All right, good. Okay, let me know when you see the screen, and I want to turn off my video.
Cool.
Video would just see the, I don't need to see me, just the application. Do you see?
Yeah, we can see it.
Okay, and then let me go to start slideshow. Set up slideshow from the beginning. Okay, there we go. Do you got a full page now? Or is it divided? If it's divided, where did it go?
Do you have two monitors by any chance?
No, where did it go?
Okay.
How do I fix that? I gotta fix that.
Hit the from beginning button again.
Let me try it again. I do have two monitors, right? On my screen, I see on the big screen, I see the correct one.
Gotcha. I think you're sharing the other screen actually. So at the top,
okay, you are sharing. Okay.
If you hit stop sharing.
I see green. You are sharing. Is that the green one or here? New share?
Yeah. And then choose the other screen.
Oh.
And that'll share.
We got the right screen yet?
Perfect. Yep. There it is.
Okay, good. Okay. So as I mentioned, we're going to be covering a lot of material. There's 40 slides here. We'll see how we do. And if we get little or no questions done, now why is my mouse not working here? You see my mouse where my name is?
Yeah.
Okay, good. So I'll send you all copies, or I'll forward to Alex the current copy, and he can distribute it. And you can just email me for further questions. So let's begin. So this is basically for the design of a conventional loudspeaker, which is, using passive crossovers, but it applies to also active systems. But passive crossovers is what I've really been doing 95% of the time. And I say I've done countless systems. So anyways, so we're first going to discuss loudspeaker directivity in the listening room. Oh, can you hear me okay?
Yeah.
Okay.
More volume or?
Right. And then we're going to talk about loudspeaker linearity. We're going to touch on the design goals, touch about transducer design and selection, go through the important teal small parameters, then transducer measurements, and the enclosure design and construction. And we're going to touch on loudspeaker crossover design, at least give tips for passive crossovers, system measurements, and then very useful web sources. Oops. So basically, first we're going to talk about directivity. Directivity is a term to describe the way a sound source frequency response changes at off-axis angles. So basically, oops, I do that. So basically, we're referencing the on-axis and how the sound changes off-axis. So where directivity speaker would be typically one that maintains a sound, constant sound on and off axis. So they say the popping sound of a balloon, maybe a gunshot. And then a narrow directivity speaker, one where the on and off axis are dramatically different, such as a bullhorn. So for a loudspeaker diaphragm, notice we have multiple diaphragms, of course, in loudspeakers, but for a loudspeaker diaphragm, so as long as the source remains small relative to the wavelengths, the frequency response radiation will be omnidirectional, and there'll be no change in the frequency response on and off axis. Of course, as you go up in frequency like a light, when the wavelength changes relative to the sound source, the radiation sound begins to beam. So one of the trade-offs is, oh, by the way, there's constant trade-offs in loudspeakers. So the larger diaphragms are required for low frequencies and for efficiency. Efficiency is related to the cone area. So we need larger diaphragms for maximum efficiency and maximum volume displacement. And smaller diaphragms are required for high frequencies for a wide radiation pattern also, such as tweeters. That's why tweeters are small. They have good wide radiation patterns, although they're not as efficient. So take the drawing on the left. So this is when you're typically set up two loudspeakers, good old stereo, which I still really enjoy. Basically, you're hearing you're hearing first the direct sound, and that's arriving to you first. And that kind of is a quality of sound that you're going to basically achieve. But then there's multiple reflections that basically arrive maybe 10, 15, 20 milliseconds later, depending on where the reflection's coming from. And these reflections are very important to be, because I'll give you an example. Like I remember years ago, I heard this string quartet in a park, and not very good detail on the sound. Then I heard the same quartet that we used at our holiday party, and it was in a typical listening room, and the sound was much more detailed and interesting because, of course, a lot of the higher frequencies, these speakers are directional too, are then reflected off the sidewalls. Primarily, you pick up lateral reflections and you get the good quality sound. So this is a very important slide. Actually, every slide can be a separate discussion for an hour. So remember this, because I constantly have this challenge every day, is that a loudspeaker is inherently a nonlinear device. So to produce the sound of live music, I'm not talking about rock concerts, I'm talking about symphony orchestras and acoustic jazz. If you think of the quality of acoustical instrument, I remember just going up to the piano in a music store and just hitting one note, and just the texture of the sound, the initial crack of the dynamics and the decay, that one note, I have yet to hear that on any accurately reproduced on a loudspeaker. And because a loudspeaker, as it moves, it's not a linear device. It's not happy to be linear and moving. So Clipple, if you've heard of it, and I have the link to the site, is encyclopedia or college of a wealth of information of loudspeakers and loudspeaker nonlinearity, and the link is there. So let's look at the model of a loudspeaker. Here's a typical entry-level high-fidelity driver. This is the one from the Revel Concerta. So loudspeakers can be modeled as electrical circuits. They're actually high-pass filters. They're actually very limited bandpass filters, but the high-pass filter is important because that's going to determine, of course, how the sound, the low-frequency response is. So if you look at the model, first you have the DC resistance of the voice coil. And this is very important because a loudspeaker with passive, or even if you EQ it, but with passive device, with passive crossovers, it's constant voltage. So its impedance varies widely with frequency. So you have to pick the proper resistance of your coil. And typically they average 3 to 4.5 ohms with passive loudspeakers. You can tend to get the best voltage and current balance. Now, one big nonlinearity is that you're basically putting the coil, you can see my cursor? Yeah, you can. Yeah, so basically, you're putting the coil in a magnetic field. You have a constant DC direct flow magnetic field, and you get eddy currents. And eddy currents are parasitic AC currents in the coil, and this actually causes distortion. And as it moves, it has nonlinear distortion. Then you have the important point of changing from electrical to acoustic, and forces flux times a length of coil times the current, or the amount of material in the cap times the current. And then it basically converts from a mass spring damper, mass being the mass of the cone, and spring being the suspensions, and the damper being the stiffness, the resistance of the mechanical stiffness of the loudspeaker cone. So this is just a simple model of the same basic entry level, if you will, high fidelity loudspeaker. And as you know, there's so when the flux flow through the coils, here we're talking about the important flux through the coil, which, as I mentioned, that is powering your loudspeaker, and that the loudspeaker, especially at low frequencies, need to move a volume of air. And the loudspeaker is not linear. As soon as the loudspeaker starts to move, it starts to move B. And typically before the Klippel device was that where you basically weren't sure what happens when the coil moves back and forth, because there's also fringing flux, which isn't symmetrical. We basically found that a lot of coils, even so they're physically centered, because of fringing flux, they weren't centered. And that means when they move one direction, they're basically losing too much flux, and losing flux, and too much flux going the other direction just produces nonlinear distortion. And with that, for example, here is a refined driver from Klippel, and you see now at least they're mirrored. You are, yes, losing flux, but you reduce some of that third harmonic distortion. So the big point you need to know is shorting range. This is important because it's constantly used on the better drivers. So what are we going to do about the parasitic AC flux? Is basically shorting, like shorting a battery, or you're basically canceling the by putting a ring in. Ring could be cut into various parts of the transducer, and you're basically then you're cutting back on the flux, on the modulated flux. So you take away the AC, and you see with and without shorting ring, you basically linearize the inductance. For a tweeter, so a similar type of situation, we have something called a copper cap. This is a little different. This is basically fixing the inductance modulation. It's basically treating a voice coil as a primary winding of a transformer. And if you short the secondary winding with a single turn, you're basically improving the current flow. And if this didn't have the copper cap, basically you'll see, this is drawn in, but you'll see basically more of a curve. You'll see a nonlinear inductance model, and as the coil moves, the induction changes, and it changes the frequency response. So you add a copper cap, you get a much flatter response. The trade-off is you lose a little bit of flux, which means you lose a little bit of output. So did I say everything has a trade-off in loudspeakers? Or it does, no matter what we do, it seems like affects something else. But overall, it's an improvement. Obviously, it's an up cost. Another place of our situation of nonlinearity, a lot of nonlinearity, is in the spider and surround, of course. So one point, you need the suspension. You need the spider is very important because it keeps the gap in place, and you have a very tight gap between where your bobbin is, and it keeps the bobbin from rubbing. So it has to be well designed. But it's nonlinear, which means as it moves, the stiffness increases. And then as it increases, then you're causing nonlinearities, and they're not symmetrical. And even the surround, you need a large roll surround. That's why it's hard to have a one-stop driver, why you see multi-way drivers, 3 ways, and even 4 ways. And with a 2-way driver trying to cost to a tweeter over a wide bandwidth, then the surround has resonances, and it's nonlinear too. So that's another point of nonlinearity. Another point, a whole separate field of nonlinearity, is the loudspeaker to produce the waveform fidelity, which I was talking about. The loudspeaker diaphragm has to be pistonic, which means it has to move as one whole piece, but it doesn't. The loudspeakers have various resonances in them. They're limited in their bandwidth depending on the diaphragm material or design. Stiffness, damping, and mass is going to affect it. So the Klippel has basically, if you look at, here's a test of a typical 6-inch woofer, and which means the acceleration is constant and there's no breakup, which means you produce a perfect output. But as you see, this is kind of an ideal model. Usually you'll see even more problems lower down. But as you see at a certain point when the loudspeaker starts breaking up, like snapping, and you see the colors here, basically blue is positive, red is negative, it becomes inefficient, which means some of the diaphragms moving opposite directions, the surround could be moving opposite direction, which it does, and then you're causing distortion and you're not getting linearity. So one of the very, very common designs in a conventional, traditional moving coil loudspeaker is a 5 or 6 inch two-way, which we call a bookshelf. Even so, you don't put them on bookshelves. We still keep that name from the 1960s. So for your design, you can do a 5 or 6 inch bookshelf, or you can do a floor speaker. So here again, we have what is from the Revel, I'm showing basically the Revel Transducer Technology, good, better, best. So here's what we say, a conventional moving coil loudspeaker, and got to move a little faster. Anyways, it's just very conventional design. And unless I'm going to now talk about cone materials. Now, cone material is something, of course, that the end user sees, and it does play an important part. So the cone technology progression, I remember when I just started getting into this industry in 1969, 1970, everything was paper. And of course, paper doesn't sound, initially paper wasn't very sophisticated. And the problem with conventional paper, which is thermoformed, is that it had inconsistency and it can absorb. In the mid 70s, KEF introduced Beckstring cone, which is basically a plastic cone, which basically was more consistent, although it was a little soft and too heavy. And then a big step was polypropylene cone, which is still used today, which is more consistent. It's not as heavy, although it's not well damped. And then in the 1970s, KEF introduced Kevlar. Of course, that was a nice yellow material that had a good story because it was used in bulletproof vests, and it was very stiff. Although stiffness and damping can be inversely related. If it's too stiff and not damped, you can have big problems with breakup, so which we'll touch on later. And then there was what Revel uses is metal cones. Metal cones got very popular because aluminum is inexpensive to form, it's very consistent, has mid-fi, upper mid-fi qualities. Then there's titanium, which is even much more stiff, very high tensile strength, but heavy, and has more breakup. And then there's different hybrids. One invention that Harman did is that they took aluminum and they high anodized it and increased the damping, and that's Revel uses that, and they're less expensive drivers. Now we're going one step up. Oh, by the way, this one here is a conventional 1 inch or 25 millimeter. When you go pick a driver, you'll see the starting sizes typically is 1 inch. I wouldn't go, definitely not go smaller than 1 inch, even in a tweeter for power handling. Then if you step up to a larger voice coil, of course, your power handling is better. Bigger voice coil, the power handling is, but then you get into a bigger magnet that costs more money. And you see in this case, it's vented. We've actually put here in this is the, put in our Performa, we actually have a copper cap and flux modulation ring combined, which is a little less cost and it works. So this lowers distortion in the low frequencies and higher frequencies. And this is a 1 1/4 inch coil, which you'll see. So then you'll see a 38 millimeter 1 1/4 inch coil. Those are the improved drivers. And then when you get to more, there you go. Oops. Oh, there you go. So this would be the Revel Ultima. Now you go and basically almost cost no object. So now we go to a neodymium magnet, which is just more efficient. A ceramic magnet is kind of sloppy because a lot of it is wasted, although it has really trade-off improvement over neodymium. It has better heat sinking, although I've seen our Pro uses neodymium with heat sinks actually on it. So with the neodymium, since it's so efficient, you put a small slug in the middle. And then this, of course, has extra cooling events. The woofer has the copper cap. And this is the woofer has a copper cap. And then the mid-range would have the modulation ring. The woofer has the shorting ring, and the mid-range has the copper cap for upper frequency inductance to linearize it. So this is kind of like a cost no object. So let's look at tweeters, entry-level tweeters, which you'll see is neodymium, and actually tiny neodymium tweeters have the least effectiveness in compression, which means they have high compression, but sometimes for size and price, these tend to be the best priced tweeters. You almost always see them in the smaller system like Sonos makes, not just Sonos, but just small loudspeakers, which doesn't have room for big ceramic magnets. And then this little tweeter is, which is more unusual for its design, is it's vented to lower the mechanical impedance to get the mechanical resonance away from below the crossover. And this also has a waveguide to control the directivity. Now at Harman, we use waveguides in our tweeters. So a waveguide, basically the easiest way to understand it is when you basically go from a large diaphragm driver, like a 6-inch, to a tiny 1-inch tweeter, you're going to have a directivity discontinuity like this picture here. And we mentioned about how important the side reflections are. You don't want a big step in discontinuity because it's going to color the sound. So if you put a waveguide in it, the civil wave waveguide is you're kind of pushing the sound forward. But we have a program where we look at the convergence angle and what type of shapes we want to get to what type of performance. Another really neat thing about a waveguide, because you're pushing the sound forward, is that you're making it more efficient. So you're actually putting the power where you need it. So look at these 3 responses here. I'll discuss them further: listening window, in-room, and sound power. You're getting more efficiency. So that's free almost. Yeah. And that obviously reduces heating of the coil. So then we go to a step up now. Now we go to ceramic magnets. One reason is that we want a large vent, and we want to lower the mechanical resonance of the driver. If it didn't have if it had no vent, you'd have the resonance at about 1500 hertz, 2000 hertz. And for passive speakers, especially, and ferrofluid, when the mechanical resonance, or the impedance can change, it could have changed the crossover. And even in an active system, you don't want to be near there, because it's also the frequency response is less consistent from unit to unit. So having a low mechanical resonance is superior. And this one now has a copper cap, which again, that's why you see a flat inductance and not a rise inductance, is an improvement. Now here's the ultimate, maybe that's why we call our speaker the Ultima. So this has basically double ceramic motors for maximum output, and it has a pin to reduce secondary resonances, a copper cap. And one feature we have here, we talked about the cone material, is beryllium. And for those who don't know beryllium, if you look it up, like Revel uses it, and Focal and others, and it's very expensive to use. This 1-inch dome of aluminum would be about 15 cents. Of beryllium is about $20. Now, why? And that increases the price, by the way. When you work in manufacturing, you'll find if you add X dollars to your design, it's going to be 5 times by the time it gets to the consumer, because everything's marked up. So why use beryllium? Well, when we want to talk about the 3 mass, stiffness, and damping are the 3 important products for a driver. If you compare beryllium to other designs, first of all, density, which is mass, beryllium is by far the lightest. Crystallized diamond, which is what BMW uses, has the highest speed of sound, which means highest point till it breaks up, even higher than beryllium, but it's twice as heavy. And Poseidon's ratio, stress over strain, is superior too. Here's an experiment that I did back in about 12 years ago, where I just had a butterfly. That's the tweeter section of the tweeter dome section. And I was first, if you look at the green curve, I was using aluminum, and you see there's a breakup at 22 kilohertz. When I went to beryllium, it was 3 dB more increase. That's the main improvement. That for tweeters, of course, they're delicate, and you want to reduce compression. And you say, well, the breakup's gone at 22 kilohertz. Well, it is a bit of a controversy, of course, when perhaps you can't hear up there, but the transient response is better too, which means it rings less. And at least the listening experience with beryllium is universally very favorable. Now, it's important when you pick your driver to measure a driver, and you want to eliminate any diffractions, or you just want to measure the driver alone. And you see I have till 12 o'clock?
Yeah.
Okay, good. I'm doing fine then. You want to make basically, well, let's go back to what we have professionally. Of course, you see we have a half space chamber. So basically there's a floor under here. It's a subfloor, and then we can put various driver sizes in here. And then we have acoustical absorption here by a company that makes anechoic chambers. And so basically when it radiates like a light, you're basically just radiating with no reflections or diffraction. Even when I measure tweeters, I even tape up these edges because even they're almost like slots can produce resonances in it. So you just want to measure the driver. And when I started with Infinity, we had an IEC baffle. That's one thing you can build. It's basically a large baffle where you can put drivers in. Of course, it's not going to be very effective at lower frequencies, but if we're looking at upper mid to high frequencies, it works quite well. So that's the way to measure drivers. So here's going back to that entry level, what I call high fidelity loudspeaker from Concerta, which basically has aluminum, which is stiff. So very, very well controlled response, as you notice. This is looking at 0, 30, and 60 degrees, by the way, which is what you can do also. Just don't look at what angle, because a loudspeaker can change dramatically due to reflections and diffraction. So basically, if you look at a lot of the data from manufacturers, they'll have at least those 0, 30, and 60 degrees. But if you look at 5.5 kilohertz, you'll see there's a big breakup point here, very high Q breakup point. And this actually even picks up a little bit distortion at the lower frequencies because the third harmonic of 6, so 1.5, 3, 6 kilohertz, that's what third harmonic, so you can pick it up in distortion. So, this is a bit of a trade-off, although, it fits its price point, it's still a terrific material to use. And how powerful the impedance curve is, which you can buy various devices, can measure impedance curve. Look at the impedance curve, you see the breakup here. And you also see the little edge hole effect here, which is what all loudspeakers have. It's basically where the outer part of the cone moves out of phase, and surround moves out of phase with the cone. And there's a little bit of a discontinuity here. You see a little drop here. And there's a little resonance here, which is probably, if you scan the driver, it could be rocking. So, and here's, of course, the mechanical resonance of the driver, FS. So impedance curve, which can be very simple, gives you a lot of information. So the Concerta 2 1-inch tweeter. So here's why one needs to measure at various angles. So at first of all, 0 degrees, it's really just a reference angle. First of all, you have 2 ears, and you're also in the center of the driver, so you're seeing equal diffraction, even from the waveguide or from edges. So you see a lot of dips and peaks here. But if you go 30 degrees, which basically counters reflections, you'll see virtually a straight line. So that means that it's not a resonance in the driver, it's a diffraction issue. Then, of course, 60 degrees is a straight line, same issue. Notice these bumps are gone, so it's just reflections that you're getting on axis. And the impedance curve, of course, shows you a pretty clean impedance curve, has kind of a broad resonance, and has a bit ferrofluid. Ferrofluid just really damps the resonance. So the importance of ferrofluid, of course, is it decreases failure quite a bit, especially when you do thousands of drivers, because it keeps the coil centered, and it also, of course, can puts the power like a heat sink into keeps the coil cooler. The downside is, as it heats up, the viscosity changes, and so having it at kilohertz even is a little high, because the viscosity changes and the frequency response changes. So, as I said, there's trade-offs and everything, but you got to pick obviously the more important one. And certainly at this price point, the small neodymium motor, we want to have ferrofluid. So the Teal small parameters, gosh, I just can't. Okay, first of all, the Teal small parameters was basically pioneered by was it Neville Teal and Richard Small in the 1960s. Basically, they looked at a loudspeaker as electromechanical device, which means they can model it as a circuit. All I can tell you about the Teal small parameters is make sure you know them really well, because most likely when you go for an interview, you'll be asked about them, because it basically sets the design of how your loudspeaker is going to be performed in this enclosure. So some of the parameters here that are important here is, of course, if you look at SD, which is the approximate area of the diaphragm, and it's about the cone and a half the surround, it's going to pick your efficiency. The DC resistance of the voice coil, which, as I mentioned, which is important to specify to the manufacturer, because that basically is going to determine, basically you have to design around the amplifiers being used. The moving mass, which of course is weight is going to affect efficiency. Compliance, of course, affects your mechanical, your resonant frequency. This is an important one, the mechanical resistance of the driver suspension. You should look for a high mechanical resistance. We had a problem with the driver that was rolling off, had a dip at the knee, and it had the material of the surround wasn't good, so did have enough damping in it. And the voice coil inductance, which is going to determine your frequency response, of course, because the inductor affects frequency response. BL, which is an important one, and that's the flux of the magnetic field strength. They call it number of turns in the gap, but it's really the amount of metal in the gap that is going to determine your force. And so here's resonant frequency, as we discussed, of course, is typical formula, mass time compliant. Electrical Q is important because you want high BL means you have a good motor. Low QE means you have a lot of damping, that you have a good output. And you want a high QMS, because the QMS, again, is going to, you don't want the knee to be weakened, because that takes a lot of the impact away from the driver. So typically, you got to look for a high QM. QTS is a total. VAS is an important one too, because I look at VAS, I know what side, if it's a small driver, large driver, because it's the SD is a big factor. And there's large signal parameters. So in the past, we were just looked at, and the way to do it too, a simple dirty way without clipple, if you will, is to look at the voice coil length and the top plate thickness, and you basically divide them. You subtract them and divide by 2, so you'll see what the overhang is. So typically you see in a 5-inch woofer, you'll see about anywhere from 3 to 6 millimeters. Subwoofers, you'll see 10 to 15 millimeters overhang. That's a start for determining what your linearity is. Of course, it's not showing the non-linearities. And then a whole separate field is power handling of the driver, which is a thorn for manufacturers. Of course, we want good power handling because we don't want the speaker to fail in the field, and we do 100-hour tests with IEC standards. Okay, so how to measure teal small parameters. It's important to get a very clean measurement when you do that. So you basically, of course, you'll have some type of device. You can buy an expensive device that can measure the impedance curve with and without added mass. So you very carefully, and you suspend the driver. In this case, we actually have a hook, and then we put a weight on it because you really don't want the driver moving. And then basically measure the driver without mass, and you carefully add the mass, typically around the dust cap. Remember, if you're a lot of cones, you got to ruin the appearance when you do this. So we have, of course, extra samples when we do this, because it doesn't affect it acoustically, it just affects the appearance. And you carefully measure the added mass, and then your program will calculate the teal small parameters. So here's an example of the calculated teal small parameters of that entry-level driver, the Concerta M16. I'm looking at this now, QTS of 0.5. I don't want to go through this too long, but I know that's approximately the range I'm looking for. The same thing with the VAS, and these are important ones. QTS, VAS, and moving mass, which are the ones that are the most tricky to calculate, because you have to make sure you do the measurement well. Are some important measurements. Of course, BL is also. By the way, Clipple has a much better system where it uses a laser and you don't have to add mass. Another important is sealed box versus vented boxes. There's no free lunch, which means, let's say this is 40 hertz, 50 hertz, which is what you're going to get in a small box. If you extend the box, yes, you do get base extension, but then it loses its impact. So when it's a constant voltage and it's not active, you don't have parametrics. You're basically doing the trade-off there. And why you see 90% of the speakers out there are vented is because the vent augments the low end. As you see, this is about the same speaker when you add a vent. If you look at this green curve here, which is like optimal, or the violet curve, you get more base extension, and the penalty is, of course, it rolls off below vent tuning. It rolls off out of phase and can increase the distortion, but we control it with the proper compliance. So when you build your box, by the way, the most common material used for the last 40 years, even changing to other materials, exotic materials, typically almost all manufacturers use 3/4 inch medium density fiberboard. You can maybe use try more exotic materials, marble, whatever, but they break and they're hard to manufacture. They're hard to finish. So just good old 3/4 inch medium density fiberboard. Of course, you don't want the enclosure to produce its sound. You want it to be as inert as possible. So to well brace it, basically we use the picture frame brace. We can use glue blocks, which secures it quite well. And another point is that if you we need to stuff the box. So when you get your microphone and a measurement, you do a near field and just measure the woofer and the port. As I say, I do recommend the port. And it's interesting what the near field shows up. If well, first let's discuss what happens when you put damping in. Notice these high Q resonances here in red. So this is just using Dacron, which is like what they stuff pillows with. Fiberglass is a little better, but it's just hard to handle. Some people like me find it just too itchy, but I get good results with fiberglass. So we see that, Dacron. So you see the Dacron is taking out the resonances. And you notice also at the time we're looking at this is that the advantage of a port is as one goes down in frequency, so you sweep down in frequency near port tuning. A port's a Helmholtz resonator. Fortunately, the pressure in the box becomes very high, and basically the woofer transfers basically all its work to the port. So if your port is well designed, you can actually lower distortion because a port can be more linear than a woofer. That's why you see a minimum here. That's where your port tuning is. So here's where, this is a little tricky to do, but in near fields, you can sum the port and the woofer. Of course, you flare the ports a little harder, but by the diameters, you can scale them. And then summing them, you can get the response of your speaker system. Of course, when you go outdoor and measure, you can get some good results too. Although it's another long story is that it's, especially with bigger speakers and multiple woofers and ports, it's very hard to get an accurate true field measurement of a loudspeaker, even in big anechoic chambers. So once again, the power of system impedance. I look at this right away and I know, well, it's got a secondary radiator, either a port or a passive radiator. And once again, this is just the woofer, no crossover. I see the resonances here. Here I can see going down in frequency, the woofer resonance. And then as I say, the woofer transfers all its work to the port. So you get basically a low back EMF where the phase angle goes through zero crossing. Minimum resistance is your port tuning. And we see we're down to about 4.2 ohms. You got to watch your impedances. Of course, some amplifiers, if you go down to below 3 ohms, they're not happy. That's why you got to look at the phase angle too, because with the phase angle, I think it's the sine or cosine. I think it's a sine of 20 or 30 degrees. You got to multiply that less than 1 times your resistance, and you'll see that it's actually lower than 3.8 ohm. So since we have a 4-ply chamber and a 2-ply chamber, in the 2-ply chamber, of course, as we saw before, you get the woofer looks flat. When you put the driver in the, I only got 10 minutes left. So anyway, you put the driver in the enclosure, you'll notice that you typically lose up to 6 dB because now you're radiating to full space and you get a bump here. So for crossover design, as you know, for the tweeters, capacitor blocks DC, so it's going to be in series. And as you go up in frequency, it passes through. An inductor is the opposite, so you should put in parallel. So this is a second order electrical. And the woofer is a third order electrical with a trap to try to cut the energy down here. Of course, you get into very exotic crossovers like in the Ultima, Revel's Best. You'll see these are the big 3-way crossovers. And as I say, this is a whole separate subject on what parts to use, inductors, capacitors, resistors. We typically try to use film inductors and film capacitors and air core inductors, although a lot of times it's not possible. So there's when you can buy crossovers that have a crossover optimizer, which means I was able to ask the program to optimize these parts to fit into a 4th order Linkert-Riley. So you can see here are the raw response to the raw woofer and the raw tweeter, and then the program actually then picks the crossover parts, change the crossover parts to fit into this roll off. And then notice again, if you look at the voltage curve on the output to the drivers, and you notice here's that. So basically you have A times B equals C. So at one time it was thought that the crossovers were that you just make a second order filter and you got a second order response on the driver. You don't. C is the target, which is here. And the crossover is a correction, basically. So this is the correction curve to produce what we're looking for the target. And here's the overall impedance response of the driver of the system. Very important passive systems, because you want to make sure that, especially when you're sending speakers out to the field, you don't want to shut off amplifiers. Customers wouldn't be happy. So you got to have the right balance of impedance. You don't want too high impedance, because then you're basically going to be wasting voltage. So the most effective, and I've tested many of the competitors, 5 and 6-inch 2-way, is a voice coil resistance of 3 to 4 ohms. Is what's showing here. Same thing here. You see the two radiators, the woofer and the vent. So this is very important too. This is called the spinorama, or the CEA 2034. It's very important to notice. This was actually pioneered originally by Floyd Toole at the National Research Council in Canada, and then refined here at Harman. And it defines basically how a loudspeaker would sound. So the on-axis response, typically we use a tweeter. It's just really a reference point, because of course it's one point, and the loudspeaker's response changes as you move around. And we have 2 ears. So this is just at 0 degrees, and you see there, it's a little lumpy. So more important is the window. Basically the average of 30 degrees horizontal, which means a wide range of listeners in seating. And then plus or minus 10 degrees if you're standing or sitting, or if you put your loudspeaker up and down. So you notice the window's a lot flatter. The very important first reflections is basically giving you the balance of the loudspeaker. So this is, if you measure in the room, this is what you would get. And the sound power, which is basically treating it's kind of more of a theoretical type of thing, and more effective for the low end. It's basically taking the loudspeaker, how it radiates, complete omnidirectional in the room. Of course, the room is going to absorb the sound and change the sound. And it's a little more accurate to give you a true response at lower frequencies. And the directivity curve, typically what we want to see is an extreme would be like an MBL, which is an omnidirectional speaker. It's a high-end loudspeaker, looks like a big accordion, which basically would have almost no change in directivity. And then maybe an electrostatic, which would be vertical, which have a very high rise in directivity. We want to see a general rise, because something like omnidirectional, like an MBL, they're very room sensitive, and everything sounds big. You listen to a piano, an orchestra, the piano sounds big. So I know I'm touting. Well, of course, most follow what we're doing. And just a general consistent rise. I mean, this obviously has imperfections. Here's where there's low beam in the crossover and little discontinuities here. But for a speaker at this price point, considering what the first reflections look like, is actually quite good. And what would you do when you measure a loudspeaker? Well, you can go outside, like this picture is, high up in the air. You don't have to go that high, but so 0 degrees is your reference. If you go 20 degrees, that's almost like your listening window. I know, so it averages out most. And 50 degrees almost looks like your first reflection, 50, 60 degrees. And then go plus or minus 10 degrees vertical. And that's when you see a lot of changes due to the path differences with the crossover. Oh, okay, so this is the last page. So here's some important points to do. So how do you design your own loudspeakers? Well, I got really good news for you. Download Room EQ Wizard. It's wonderful. It's a complete measurement system. We even use it here professionally at times. You can measure in your room. You can measure outside. All you need is a PC and an amplifier. A few other things too. A great microphone, so that's free. And the UMIC measuring microphone for the REW is under $100. Price may have gone up. I don't know what it is now, but that's a steal also. It even comes with calibration. And then, of course, from Parts Express, you can look up all types of drivers, and Matasound too. You can go, SB has good data sheets. CS you can buy from, Dyna Audio. There's others too where you can buy drivers, and a lot of times they're quite honest now on the curves they give you. You'll see 0, 30, and 60, and impedance curves and other things. And hey, I'm finishing a good time. So that's done with that. So if you guys have any questions, or if not, you can email me. Hello?
Yeah. Thank you. Wow, that was a lot of information. I think we might have a couple questions. I have a question just to start off, just about in terms of like how all of this translates to if we are looking to build speaker enclosure, put a driver inside of it. What are like I guess the main thing would be like the teal small parameters, but what's the what would you look for if you were trying to evaluate a driver, just kind of really quick and dirty? Like what's the key things that you're kind of looking for?
Well, of course, you would look for, let's go to that page. Okay, so, okay, oh, there it is. So first of all, okay, so first of all, you need to curve, as I mentioned, you need curve on a large baffle. You can either put in the ground in your backyard, or you can build a baffle like this, and then you use the REW and the Umix mic, if I'm pronouncing it right. And you obviously want to see a straight line. On axis, typically you see a straight line. Off axis, it's going to start to beam. But if you notice here, there's just looking on here, you see it well controlled. Almost all drivers have a little bit of a discontinuity here. So this page is important. Do frequency response and impedance. That costs almost nothing, because you notice your impedance curve shows you the resonances too. Here's the resonance here, and here's the resonance here. So you want to basically make sure it's flat. You even want to try it maybe at 2.8 volts or 3 volts, then go to 6 volts. Make sure it goes up 6 dB, right? W voltage is 6 dB or 6 dB for dynamics. And as I say, just reference to this page, and they'll and a lot of manufacturers give you the exact same. This page here, a lot of manufacturers like SB Acoustics and others will give you this information too. That's for woofers, and then for tweeters, as I mentioned, you'd want to see the best tweeters. This is sort of, you know, more of a compromise, if you will, if you can say that. I mentioned that everything's a compromise, and you make less expensive speakers, every manufacturer and everyone's got to have some compromises, but something more ideal would be, where did it go? Am I going the right way? No. Would be reference to, oh, like this is an excellent impedance curve, because you can see that it's got, see, I can tell from the impedance curve, it's got a copper cap. We discussed that about linearizing the inductance, because it's straight. Doesn't have like a circle curve, and it's got a low mechanical impedance. So the mechanical impedance, which varies from driver to driver. And also I noticed when the mechanical impedance is higher, it's in your crossover range and the drivers aren't consistent. So you'll have, this is a superior driver. So just reference to these pages.
Thank you.
It might not be very good. Can you hear me okay?
Yes.
Okay, so when you're looking at the frequency response of, like, let's say a tweeter or something, how can you tell between, like, if you're comparing the on-axis and the off-axis response, how can you tell if you can correct it with like a waveguide, like, or if that's just the mechanical nature of the driver? Because I know you mentioned you pointed at the plot and you said, oh, this right here you can tell it's diffraction or something like that. How would you be able to tell what you can correct with the waveguide and what is a mechanical resonance?
Okay, well, okay, let's look at this page. First, talk about resonances. If that's why 0, 30, and 60 is good. You see how 60 degrees is flat, and even 30 degrees relatively flat. You see these dips and peaks here, they basically go away. You see the red curve to here. So this is a diffraction, because the waveguide or drivers, they have equal, if you're putting the microphone right in the center, so it's equal pathway to any type of discontinuity. And of course, you're not really hearing that, because you'll never have, you want to have one ear right in the center. You can be anywhere, right? That's why averaging, spatial averaging is very important in acoustics, even for like room measurements. So in this case, of course, you can either, if you have a way of averaging, I think REW does, you can say measure 0, 10, 20, 30 degrees in an average. That would be a good way. And as far as a waveguide goes, it's a little more complicated, because that would go to your, and I don't think there'd be a way of, you guys can do this. Where's this information here, which I know if you go to Audioholics, I was going to ask him, and that he has some type of portable system, and he can calculate this type of measurement. But this type of measurement, you have to measure 0 to 360 degrees every 10 degrees. That's what, 35 measurements, 36, whatever it is, and then go vertical 0 to every 10 degrees to 360 degrees. And then the program calculates with all those angles, has 72 angles. It'll calculate, of course, on axis is only one measurement, but the window, it'll average over 30 degrees. And first reflections, it'll look at 40, 50, 60 degrees off axis, and then 0 to 180. And it would do the calculations there to get first reflections. And then sound power, it also has its calculations.
So that's
But,
not something we would be able to just do like at home.
no, that's the problem. To design your own waveguide. No, you would need. Well, we have a waveguide program which is proprietary, but you can buy off the shelf speakers with waveguides. Also, if you could design a waveguide, you need, of course, you'd have to design it on AutoCAD and then get a 3D printer. I guess it can be done. And then the directivity index is very important if you understand directivity index. So you can see my cursor.
Move it around.
Yeah, you see the cursor where it says DI sound power.
Oh, yeah.
Okay, so if there was no waveguide here, what would happen is, so the woofers is getting directional. Then when the tweeter kicks in, this would basically take a dive. So basically, because it's taking a dive, which means there's a big directivity difference between the woofer, which is starting to beam or starting to become directional, to when the tweeter kicks in, it's basically omnidirectional. So then this would basically go, the directivity index would dramatically change. And a speaker with, in fact, there's a speaker, I have another paper I did actually comparing this Revel to 3 competitors. There's a speaker like this from Monitor Audio that had no waveguide, and you saw a big discontinuity in the first reflections. So it wouldn't sound balanced. So the waveguide is basically giving you constant, it would basically, I have better examples. We have better waveguides now, where you virtually don't even see a change here at all. But if there's no waveguide here, when the tweeter kicks in, this would drop way down and be flatter. Or even in the first reflections, you would see a big discontinuity here. So
Gotcha.
it's matching, it's giving you a better sound balance. And if you look at the first reflections compared to a lot of other speakers, especially without a waveguide, it's much more consistent, even if the waveguide is not perfect.
Cool. Well, Mark, I think we're kind of hitting on time now, but thank you. This was a really amazing presentation. Can I distribute your contact info if people have any questions?
Yeah, please do. Yeah, and I think you have the paper. I did a slight updates to it. I'll send you the latest, and just distribute the paper. It's open, it's open source, whatever you call it, to as many people who want it. I don't mind. I know some people couldn't attend. You can distribute the paper to them also, and they can feel free to contact me with any questions. Since you guys are audio enthusiasts, we do have, Harman is a huge corporation owned by Samsung. There's lots of audio jobs. So I think we even have a internship coming up. So, you go ahead and email me or contact our personnel. I can send you, probably go through personnel, both. And you can send me your resumes, and I think we'll be having the position open too, although it may not be entry level, but hey, who knows? But there is an internship coming up, and I'd say it worked for Anna very well, because she actually worked as an intern for us, and she got the full-time position in Nova.
Cool. Well, good to know. I expect you'll be getting some emails in that case.
Yeah, and good luck to you all. I know I was in the same boat. Yeah. It was very tough for me because the industry's actually grown a lot. I mean, now you have Google and Apple and Facebook and Amazon. They're all doing audio, so they're loudspeakers and stuff. So there's a lot of job opportunities out there. Good luck to you all.
All right. Thanks, Mark. Have a great day.
You
Bye.
too. Bye.